Hello, I'm Jad Bassil, a master's student at University of Bourgogne-Franche-Comté, and I will present to you a linear distributed clustering algorithm for modular robots-based programmable matter, which was done as part of my research internship at FemtoST Institute in France. First, I will start with an introduction defining our research domain, the modular robots-based programmable matter. Then the context and applications showing the benefits of modular robots clustering. After that, I will explain our proposed solution, then show the conducted experiments and results, and finally the conclusion. Programmable matter is a matter that can change its physical properties, such as changing its shape on demand. One way to achieve a programmable matter is by building a large modular robot made of tiny self-configurable robots that can communicate to exchange messages and move to change the overall shape of the set. For example, on the right we can see a mug made by tiny spherical modules reconfiguring itself into a plate. However, self-configuration is a complex task since the number of possible configurations can increase drastically when the number of modules in the system increases. Clustering allows parallelization, therefore it can have many benefits such as scalability, energy efficiency, and reducing the execution time of many tasks, including the self-configuration. Our objective is to propose a distributed and efficient clustering algorithm to simplify the transformation of a modular robot from an initial shape to a goal one. On the right, we can see modules in the initial shape assembling themselves in clusters of different colors. Then the clusters reconfigure in parallel to form the final humanoid shape. Self-configuration requires an efficient scene encoding. A solution based on constructive solid geometry or CSG can be used for this purpose. It defines a tree made of basic geometrical objects that when combined form the final scene. The CSG tree can be efficiently stored in each module and can be used to determine the number of clusters. For example, on the CSG tree shown on the right, we can choose the number of clusters to be 2, which is the number of objects on the level 1 of the tree. Our proposed solution is a graph clustering solution, since a modular robot can be modeled as an unoriented graph, where vertices represent modules and edges represent connections between adjacent modules. It is based on the D-cut algorithm proposed by Shao et al. In 2016 that envisions graph clustering as a tree-based density cut problem and can be divided into 3 steps. First, edges weights are calculated to reflect the density and the geometrical aspect of the system. Then the density connected tree or DCT is built to sketch the overall structure of the robot. Then the DCT is partitioned until the wanted number of clusters is obtained. Our solution is fully distributed and can be executed in a logarithmic time complexity and a linear communication complexity. Next, I will explain the steps of the algorithm. The first step consists of calculating the edge weights. To do so, we first define anchors as the set of points on the extremities of the geometry bounding box. On the example of the figure, anchors are positioned on modules in red. In order to explain how an edge weight is calculated, I will show it on the example of the edge between modules 5 and 7. First, all modules calculate and store their neighborhood denoted as gamma and defined as the set containing their neighbors' IDs plus their own ID. In addition, they store the Euclidean distance to their nearest anchor. Then the module with largest ID will send a request containing its neighborhood and the distance to its nearest anchor to neighbors with lower ID. On reception, the weight is calculated by dividing the Jaccard coefficient used to capture the local density by the minimum between the received and stored distance. The result is then sent back in response, and at this stage, both modules can store their adjacent edge weight. All weights in the system can be similarly computed at the same time and in an asynchronous manner. The second step consists of building the density connected tree, which is a maximum spanning tree. An efficient and fully distributed algorithm is used. At the end of the step, the tree is rooted at one module, and all modules know their children and the path to the root. Since the tree forms an acyclic graph, removing a cut edge will result in two clusters. The root will then initiate the search for the cut edge, which is the edge with minimum V-cut value, defined as the weight of the edge separating the two clusters divided by the minimum of their sizes to avoid splitting small sets of modules. On our example, the cut edge is the edge between modules 5 and 7. Removing it results in the green and blue clusters. The resulted clusters can then be recursively repartitioned by finding and removing additional cut edges until the wanted number of clusters is obtained. In order to validate our algorithm, we conducted different simulations using VisibleSim, which is a discrete event simulator that can support tens of thousands of modules of different types, including the 3D cutoms used in our simulations. 3D cutoms are quasi-spherical modules placed in face-centered cubic lattice. They can communicate and turn around up to 12 neighbors. Then we validated our simulations on a real robotic system called the Blinky blocks, which are 4 centimeter large cubic robots placed in a cubic regular lattice. They can communicate with up to 6 connected neighbors and lights up in colors to show their status. The video on the left shows the execution of our algorithm on Blinky blocks with different shapes and different number of modules. The blocks change their colors according to the steps of the algorithm. At the end of each step, the cluster head, which is the modules on the roots of clusters trees, are blinking to be easily spotted. On the right, we can see the result of simulations of VisibleSim with 4 clusters and 4 different geometrical shapes with different geometrical properties. We can see that the clusters follow the coordinate axis to regularly divide the space. The graphs in this slide evaluate the performance of our algorithm in terms of execution time with 2 and 10 clusters on the shapes shown in the previous slide, while varying the number of modules to more than 30,000 modules. We can see that the execution time increases logarithmically when the number of modules in the system increases, and that is valid on all shapes. On the right, we can see that additional number of clusters requires more execution time, since more cut edges need to be found and removed. It is also affected by the geometrical shape of the system. We can see that the random shape requires the lowest time since it presents a more compact geometry. Next, to evaluate the number of exchanged messages, we can see that it increases linearly when the number of modules in the system increases, and that is also valid on all the shapes. Additional number of clusters requires finding and removing additional cut edges. Therefore, additional number of exchange messages is needed. The geometrical shape also affects the number of messages. We can remark that the random shape requires the highest number of messages since it presents more connections in its system. To conclude, we proposed a distributed algorithm based on the D-cut algorithm to cluster large-scale modular robotic systems in order to improve the self-reconfiguration process via parallelization. The performance of our algorithm is affected by the number of modules in the system, the number of wanted clusters, and the geometrical shape of the system. In the future, we aim to control the number of modules in each cluster which is crucial for the self-reconfiguration process. Then extend the algorithm to support dynamic clusters since modules can always change their positions. After that, we aim to study cluster-based method to enhance the self-reconfiguration algorithms. On the right, we can see the result of an early work as a proof of concept, where clusters of sliding blocks are reconfiguring in parallel to form the final goal shape. In the future, we aim to extend and generalize this concept to support a wide range of robotic systems. Thank you for your attention. Feel free to send me your question by mail to jad.bassil@femto-st.fr. You can find additional information on the Programmable Matter project's website and additional videos on the Blinky blog and Visible Sim at the OmniTeam YouTube channel.